So hi everyone, in today's lecture we are going to derive Klein-gordon equation. So in 1926 Erwin Schrödinger proposed relativistic wave equation. So this equation was known as Klein-gordon equation. So it describes the relativistic motion of spin zero or spinless particles. So it is applicable to the particles like pi mesons. The wave function phi of r comma t depends on position and time. So let us proceed with the derivation. So in order to derive the Klein-gordon equation, we are going to consider the Schrödinger wave equation. So the Schrödinger wave equation is given by h phi is equals to E phi. We are going to call this as equation 1. But the Hamiltonian H is also given by T plus V. Here T is kinetic energy and V is potential energy. So the expression for kinetic energy is P square by 2m and the expression for potential energy is V of R. We are going to take potential energy as V of R. So if we substitute the potential energy and kinetic energy terms in the equation 1, so the equation 1 becomes P square by 2m plus V of R into phi of R comma t is equals to E into phi of R comma t. So now what we are going to do is we are going to consider the momentum operator. So the momentum operator is given by minus I h cross into del and the energy operator is given by I h cross dou by dou t. So we are going to substitute these two operator equations in the above equation. So the above equation becomes minus I h cross del divided by 2m plus V of R is the potential energy and the wave function is phi of r comma t and the energy will becomes I h cross dou by dou t into phi of r comma t. I missed a whole square here. So this equation can be written as minus h cross square del square divided by 2m into phi of r comma t plus V of R into phi of r comma t is equals to I h cross dou by dou t phi of r comma t. So we are going to name it as equation 2. So if we observe equation 2, we can see the equation is second order in space. So with the del operator we can say the above equation is second order in space, and if we observe this dou by dou t term we can say that is the equation is first order in time. So in order to call our equation as relativistic, then that equation should be same order both in space and time. So for an equation to be called relativistic, it should be same order both in space and time. So but this equation is second order in space and first order in time. So we cannot call the equation 2 as relativistic. So what we are going to do is we are going to consider the relativistic energy equation. The relativistic energy equation is E square is equals to P square C square plus M square C power 4. So same what we are going to do is we are going to substitute the operators I h cross dou by dou t whole square is equals to minus I h cross del whole square C square plus M square C power 4. So so the I whole square will be minus h cross square dou square by dou t square is equals to minus I whole square also gives minus h cross square del square c square plus m square c power 4. We are going to take this term to the LHS, then it becomes h cross square del square c square minus h cross square dou square by dou t square is equals to m square c power 4. So if we take h square c square as common, then it will become del square minus 1 by c square dou square by dou t square is equals to m square c power 4. So this c square will cancels with this c. Then if we send h cross to the RHS, then we get del square by 1 by c square dou square by dou t square, and we are going to multiply the wave function is equals to m square c square by h cross square. So now we can observe the del square is second order in space, and the same dou square by dou t square is second order in time. So both space and time are of same order. So we can say this equation as the relativistic equation. So if we substitute another operator called del, then this equation becomes m square c square by h cross square. So here the operator del is known as D'Alembert operator, and it is given by del is equals to del square minus 1 by c square dou square by dou t square. So if we write the final Klein-gordon equation, then that equation is of del phi of r comma t is equals to m square c square by h cross square phi of r comma t. So this equation is the Klein-gordon equation. So thank you.